Part 2, Angular Momentum. Now we looked at an object that was simply just spinning. Now we're going to look at an object that goes around something else. So what I've got here is two masses that are exactly the same, and I've got this one right here. It's attached to a string, and it's going to rotate around this dot right here. So it's going to go around the circle like that. Alright, so it's going to go all the way around that circle when this guy collides into it and sticks together. So it's going to have an inelastic collision with this ball, and then they're going to stick together and go around the circle like this. So then they will move together around the circle. Now, if the momentum is conserved, we want to answer a few questions. How fast are they going immediately after the collision? Now, I'm talking about linear momentum first. So how fast are they going straight up on this page first? Then we can think of things, how fast is it going around the circle? How long does it take? We're going to answer those questions. So first of all, how fast does it go straight up? Then, how fast is it going to go around the circle? So here are some values that we can play with. We have the initial velocity of 5 meters per second. Both masses are 3 kilograms, and the radius is 2 meters. First question we are going to answer is, what is the final velocity? And I'm talking about linear velocity, not angular. So I'm talking about this one. So immediately after they collide, how fast are they going that way? Straight up. So this is a simple momentum conservation question. We can already do this. We don't have to factor in rotational momentum yet, because this is the instant they collide. So they're not really going around the circle quite yet. They're still going in the straight line. So it's just initial momentum equals the final. And M1, V1, easy. We know both of those. The other one's at rest, so it's plus 0. Then they move together as one big object. So I need to add them together. And then that is moving at a final velocity. Now, well, this is a no-brainer. We just have to solve this for V prime, and we're done. And I know all the masses. They're all the same. And I know the initial velocity, so this is easy. Now, if it was originally moving at 5 meters per second, and it collides with an identical mass, so in other words, the mass doubles, then the velocity should be cut in half. So it should be 2.5. Well, let's see if it actually is. So 3 kilograms times 5 meters per second divided by 6. So divided by the sum of both masses, that's going to be 2.5. Well, that's less, definitely less than what we had before, but 2.5 is exactly half of 5, so it went down by a half. So this is pretty easy to visualize here. If this goes up and this stays the same, then this has to go down, because if I multiply by a bigger number, I need to multiply the velocity by a smaller number. So if the mass doubles, then the velocity gets cut in half, which is exactly what we saw here. Okay, so what's its angular velocity? Let's think about this. How fast is it going around the circle? Well, we can figure this out because we know that velocity equals r omega, and we'll solve that for omega, or as you like to call it, wumbo. It's got a radius of 2 meters, and it's going 2.5 meters per second. This is an easy calculation. So we have an angular velocity of this, 1.25 radians per second. So what's its angular momentum? All right, so different thing we're thinking about. What's its momentum, not in a straight line, but what's its momentum around the circle that it spins around? So we derived before sort of a hand-waving derivation, but nevertheless it was a derivation, and it was mass times velocity times radius, which is basically momentum times radius. So let's do that. Mass times velocity times radius. And there we go. So we got the mass of, let me point out this is 6, not 3, because it's both objects moving. So we have both masses totaling at 6 kilograms and moving this fast, 2.5 meters per second, and a radius of 2. Multiply all that out, there's your angular momentum, 30. So how long does it take to go around the circle? Now we can keep asking questions and keep calculating. Just showing you like what you can do as you work through kind of these calculations here. This angular velocity we do have already in radians per second, and theta is 1 revolution. In terms of radians, that's 2 pi. I got a little messy, I apologize. So yeah, 2 pi radians divided by 1.5, or 1.25 radians per second. So our angular, our period here is 5 seconds. Now, we found all that, but let's make a comparison with a very similar situation, but I'm only going to change one thing. First, we had a radius of 2 meters. Then, what I'm going to do now is, how is everything going to change if I double the radius? Make it twice as big. So we're going to find out what's that angular velocity going around, what's the linear velocity, and then what's the new period got to be? Well, it's still going to be the same collision. Let me back up here. It's going to be the same collision. It's still 3 kilograms moving at, so we got 3 kilograms moving this way, colliding with another 3 kilograms that's at rest, and they stick together. Well, their linear velocity is going to be the same. It's still going to be 2.5, but what's different is how it moves around the circle. So the radius is 4 meters. That's a change, but the masses are the same, velocity is the same. So our angular momentum is just mass times velocity times radius. So 6 times 2.5, and now times double the radius, so that means our angular momentum is going to be double of what it was before. Alright, so we have twice as much angular momentum, yet we still have the same linear momentum. So we still ended up at the same velocity, but angular velocity is probably going to be different. Now, we had our angular velocity, or no, excuse me, our linear velocity of 2.5, and radius is now twice as much. So now our angular velocity is going to be half as much, because we have to go around a bigger circle. So if we go around a bigger circle, then suppose for a second you could think of, try to predict what the period would be. Well, the period is still 2 pi radians. It's still the same, as far as angles, it's still 2 pi radians. That has not changed. But our velocity is half as much. So if we're going around the same angle, but half of the speed, then we're going to have twice as long as a period. So it'll take twice as long, which makes sense. We're going half as fast, it'll take longer. We're going twice as fast, it shouldn't take as long. Okay, those are all the examples for now. Now, if that was a very long set of examples, so if you need a refresher, bring your questions to class and ask me in person, or you are always feel free to watch these again.